This is Lab 2, Lines of Charge. This lab is a continuation of the experiment done in Lab 1, but now we are treating the charge tapes as a line charge instead of as point charges. This means that the charge is distributed along the length of the tape instead of concentrated in one spot, and this will affect our later calculations. As we did in Lab 1, we will be creating charge tapes, observing interactions between two charge tapes, and then doing calculations to find excess charge on the tape. Like in Lab 1, we can assume that each U-tape has roughly the same amount of charge. The fundamental physical principles that we will use in this lab are: like signs repel while opposite signs attract. We will use three formulas: the gravitational force formula, the electric field formula, and the electric force formula. And we will use the concept that temporary dipoles are created in neutral objects when they interact with charged objects, and then this neutral object will be attracted to the charged object. A new concept for this lab is how to calculate the E-field of distributed charges. You divide the charge object into a collection of point charges, compute the E-field of each typical piece, and then add the E-field of all pieces to find the E-field of the charged object. In order to complete this lab, you must first create two charge tapes in the same way that you did in Lab 1. Place the base tape on a smooth surface, and then measure the upper tape or U-tape to be 20 centimeters long and create a handle on the end by folding it over. Then stick this U-tape to the base tape and quickly remove the U-tape, and you will have a charged U-tape. Repeat this process so that you have two charged tapes. Then find the distance between the tapes required for one piece of tape to levitate above the other. Use the fundamental definitions previously explained to find excess charge on the tape, treating the tapes as a line charge rather than as a point charge. The distance between the tapes required to levitate was 0.018 meters. The mass of the tape was 2 times 10 to the negative 4th kilogram. The length of the tape was 0.2 meters. The force due to the electric field was 0.00196 newtons. The charge of tape when treating it like a point charge was 8.4 times 10 to the negative 9th coulombs. And the charge of the tape when treating it like a line charge was 1.2275 times 10 to the negative 8th coulomb. Using the base code, I was able to create a computational model of this interaction. The blue circles represent the upper tape, while the red circles represent the lower tape. The green arrow is the total electric force, the yellow arrow is the gravitational force, and the white arrows are the electric fields at each point charge. The magnitude of the electric force found by this model was 0.001962 newtons. The magnitude of the gravitational force was 0.001962 newtons, and the charge was 1.2275 times 10 to the negative 8th. The first question that I had to answer about this lab was, what if you had modeled each of your tapes as a single point charge like in the previous lab? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge model to the value you got with your line charge model. The data would be less accurate if I modeled each of the tapes as a single point charge instead of as a line charge. Using the point charge model, I got Q to equal 8.4 times 10 to the negative 9th coulomb. This value is smaller because all of the charge is concentrated, so it requires less of the charge to levitate. Using the line charge model, I got Q equals 1.2275 times 10 to the negative 8th coulombs. This value is larger since some of the x direction is cancelled, while the y direction charges add up. The second question was, why do these estimates differ? Which value is more likely to be closer to the real value, and why? The estimates differ because the electric field shapes are different for the point charge and line charge models. The electric field takes a fan shape for the line charge model, which is a more accurate representation. The line charge model is more likely to be the real value because assuming the tape to be a line of charge rather than a point of charge is a closer representation. The tape is a 3D object which the charge will spread all over instead of being concentrated at a point like the point charge model assumes.